Hi guys, welcome back to my channel. Now we've actually spoken about random and systematic error a little bit in our previous video. So if you go back and have a look at 10.2 calculating error and 10.3 constructing and using graphs, or even 10.1 accuracy and precision, I've spoken about these terms a little bit before, but we're going to focus on them specifically today. So to be successful, I want you to be able to describe the difference between systematic and random error. And I think too, as a chemistry teacher and as someone who went through and did a science undergraduate degree and someone who watched other people in the undergraduate degree do some crazy, terrible, bad stuff in the laboratories, I don't want you to go through and make those same stupid mistakes. So I think maybe I should say another success criteria for today is to understand the importance of removing error from your experimental procedures. Okay, so let's go. Let's talk about this. Let's talk about the difference. Oh, I've written a little note here for myself, and maybe I should tell you about this story about what happened at university one time. So an error is not the same thing as a mistake, okay? So if you are someone and you've put something in the machine wrong and you go, oh, I realized I put it in the machine wrong, don't include that value, right? You know that you've stuffed up. There's no point including it. But if you've done everything that you possibly can and you seem to be getting these consistent results and you think, what is going on here? Maybe there's a reason for that and you should go back and investigate it because it might not actually be an error. It might just be like a strange result and you might have actually found something new. So we fix mistakes, we account for errors. And I'll tell you what happened. So this girl at university, we were measuring the concentration of different metals. And to do that, we had performed this experiment with a pipette and a bulb. And if you don't know what they look like, so if we have a glass pipette that looks like this, you get like a red colored bulb. I can't draw this very well. That sort of goes over the top. And then it has these random little like knobby things on the side. I'm not explaining this very well, but kind of like a teardrop, like those medicine drops that you would have gotten as kids to have your medicine with. So you suck it up into the bulb and then you can empty, using one of these valves, either the entire thing out at once or you can empty out very small bits, so that you get like a very precise amount of the liquid that you need inside your pipette. And so what she did, and this is what you should not do, was she wasn't really paying attention. So she had her pipette in her sample and she sucked up a whole bunch of this sample. And when she sucked up this sample, it literally went poof, all the way up into the bulb. And then when she went, oh, that's too much, and she emptied out a little bit, I saw this little like plume of stuff coming out of the bulb. So clearly what's happened is previously someone's done the same thing. They've sucked up some sort of liquid into this bulb and then it's gone up inside the bulb and it's probably going to damage the bulb at some point. And then it's dried and then when she's done the same thing, it's released all of that into her sample. And then she went to do the measurement and then she was like, my measurement for my heavy metal sample seems really high for some reason. Couldn't tell you why. Anyway, so we fixed mistakes. I would have gone back. I would have just emptied out that whole pipette and I would have taken another sample from my original beaker. I would not have just measured that. That was not accurate whatsoever. So, systematic error is a consistent, repeatable error that occurs every time a piece of equipment is used. So for example, if I had a ruler, and this is such a simple mistake to make, when you look at your ruler, sometimes rulers, they have their zero measurement right at the end of that ruler, and sometimes rulers have their zero measurements about 1/2 centimeter in. And I see students do this all the time. They'll measure from the wrong spot. So you always have to make sure that you line up with where the zero actually is before you perform your measurement. So this is an example of a systematic error because they go back and they measure it incorrectly every single time using that same piece of equipment. So this is called measurement bias. The other kind of error could be, or systematic error could be selection bias. So I'm going to say, like, if I was to go out into a big field and I'm going to take random samples of that field so I can get an accurate estimate of what's going on, or like maybe how many trees or how many koalas are in this particular field, right? So if I take this randomly all over the place, that should be pretty representative of what's going on over the whole field. Okay, but in reality, as a uni student, a little bit lazy, and I thought, no, you know what we'll do? We'll just go to this same spot and we'll just do all of my measurements right here in this corner, because then I don't have to travel over to all these other spots, right? No, that's not quite right, because that there is selection bias. If I measure only in this particular little area, I'm only going to see so much. Koalas might be chilling out over here, and I don't know that. It's like saying if I went to the ocean and I got a cup of water from the ocean and I said, there's no whales in this cup of water, therefore there must be no whales in the ocean. Well, there is, it's just that your method for selecting for whales is pretty poor. So that's a form of selection bias. Now, systematic errors are errors that can be corrected, and we can correct that by learning how to use equipment properly. We can calibrate equipment properly. So I've mentioned this a couple of times now with the scales and how we tear a set of scales, literally one button that we have to press. Selection bias, again, we can correct for this error because we know that we should be measuring random spots, not just all in the corner. Random errors, on the other hand, we cannot predict them and they have no detectable pattern. And so therefore we can't actually correct for these errors. We can do things very, very carefully, and we've spoken about this before too with like the parallax error. That's usually a common source of this random error. If you do it enough times, it becomes systematic. But with the parallax error, it's the perception error. So we've got to make sure that we're always observing things right at eye level. Okay, and not like from up above or not from like down below, because then we get those perception issues. Okay. All right, so let's go through. Oh, sorry, and one more thing, natural variation. ID10T errors, that's kind of what I was talking about before with that girl at university. Okay, so define and describe two examples. I've just mentioned those. Explain random errors, provide an example. Again, I've just mentioned a couple of those. So you can go ahead and describe those two terms. So identify the following as random errors or systematic errors. So I'm going to get you to pause the video here. I want you to have a go, and I'll come back after the break with the answers for each. Okay, so first one, there is a consistent draft pushing down on the electronic balance. So if you have a very sensitive set of scales, you guys haven't seen these scales yet, but they do have them in the labs here at school. They keep them in these like encased glass boxes, and they have like a little door on the side. And so you open up the door, you pop the scale, whatever it is, you pop whatever it is on the scale, and then you close the door, and then you do the measurements. And that's because these scales, they'll go to like 3 or 4 decimal places. They are very, very sensitive to any sort of outside pressure. Like you waving your hand over them is enough to sort of set them off. So if there's a consistent draft pushing down on the electronic balance, that's going to be a systematic error, because we can correct for that, can't we? We can just put it in a little glass box to stop that draft, or we can turn the fan off. There is an air bubble in the liquid of a thermometer. So this is again a measurement error. So this is a systematic error. We can correct for this. So if I had my thermometer here, like this, for example, if I just tap, 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 then the bubble will come up to the top, and then it will no longer be affecting our measurement. A student takes measurements from the bottom of the meniscus, the top of the meniscus rather than the bottom. So a meniscus, I love this term. This is such a fun term. So glass is a slightly polar compound. Water is also a slightly polar compound. Water is more attracted to glass than it is attracted to itself. And so what you actually see, and you guys have probably seen this, is you get this like sort of concave kind of a shape. So when we measure things, we need to measure from the bottom of this meniscus here. This has traveled up the sides due to the attraction to the glass. It's not actually increased the volume. So we have to measure from the bottom of the meniscus. If we measure from the top, it's going to be an overestimate. Mercury is actually one of these really cool substances. And mercury is actually more attracted to itself than it is to the glass. And it's because mercury is not polar. And so it actually looks like this. And so when we have something that looks like that, we should be measuring it just at that point of that meniscus there. So we should measure it at the point of that most concave part. Okay, so again, this one, we could consider this a random error if it happens once. We could consider this a systematic error if they are doing that measurement every single time. Okay, so D, the scale consistently measures 5 units above the true value, systematic. A student miscounts the number of drops in the third sample tested. Straight up, just a random error. Oh, sorry, I should put R for error. Just a random one because they've only done it once. A student does not measure the meniscus at eye level, so that's that parallax error. So again, are they doing it every single time? Because if they're doing it every single time, it's a systematic error. If they do it once, it's random. And last one, a student uses a buffer to calibrate a pH meter. So, they're calibrating. We love that. Good, good. After completing the experiment, the student discovers that the pH buffer was 6.7. So if you don't know, they use a pH buffer to calibrate. And so this should always be pure water and it should have a pH equal to exactly 7. And so when you go to measure your other things, so for example, you might be measuring an acid and you might work out the pH of this is going to be equal to 5. You know that's a accurate measurement because you've calibrated your instrument. Now, if this pH buffer was 6.7, then we would have to actually change these values as well. So I'm assuming it's going down by 0.3, so then this would be a measurement of 4.7 instead. So this would be a systematic error. Okay, so I think you guys can go ahead now and finish this off yourself. It's not too tricky describing the differences between the two kinds of error. So have a wonderful day, and I will talk to you guys again soon.